Our next speaker is Dmitry Tsepelev. He's going to talk about building high-performance GraphQL APIs. And his background is in back-end engineering at Evil Martians, open source enthusiast. Almost nailed that. And about the talk. One day you decided to give GraphQL a try and implement an API of your new application using GraphQL. You deployed the app to production, but after a while you realized that responses are not super fast. How to find out what makes your GraphQL endpoint slow? We'll discuss how queries are executed and what makes processing slower. After that, we'll learn how to measure performance in the GraphQL era and determine the part we should improve. Finally, we'll discuss possible solutions and some advanced techniques to keep your GraphQL app fast. And now remember the stream chat. You can send the questions to Dmitry via stream chat, and I'll be picking up the questions from there. Dmitry, the floor is yours.
Okay, I hope you can hear me now and see my screen. Hi everyone, and welcome to my talk called Building High-Performance GraphQL APIs. As been said, my name is Dmitry, or Dima, if it's easier. I live in a small Russian town called Vladimir, and I am a backend engineer at Evil Martians. I do a lot of open source, conference talks, and sometimes I write articles, and I show some of my articles to you today. And now we use GraphQL a lot in our production applications. So this is a talk for people who already use GraphQL in production, and it's not an introduction talk. So we're not going to talk about pros and cons. But if you need some details about the technology itself, I'd suggest you to take a look at my previous talk. It's called Thinking in Graphs. I gave it like 2 years ago, but it's still actual, I guess, so there is a link. And if you want to try out GraphQL by hand, you can take a look at one of Evil Martians' articles about writing GraphQL applications in Rails. There are 3 articles where you can build a GraphQL application from scratch, as well as a Apollo client for it. So this is a good place to start. And now we're going to start to talk about the performance. And I wanted to start with the query path that is performed when GraphQL application processes the request, because we should know the places where things can go wrong. So first of all, in GraphQL, query is just a string. We'll call it a query string. It usually comes to the /GraphQL endpoint, and this is the post request. It goes to the GraphQL controller, where we have to pass it to the GraphQL schema, as well as arguments and some other variables. Then we should pass it because we need to prepare the abstract syntax tree to work with. So we pass the query string to the query parse method. As soon as we have the abstract syntax tree, we have to validate it to make sure that it's valid. So the syntax is valid, all the required variables are passed, and so on. Then we have to execute it, and as you can see, the query is a tree, so we should go it recursively, and that's why there is an arrow on the right of the block. So this stage is called execute field, and it happens until we execute all fields. Also, sometimes we go to the data source, for instance, to the database. And there is one trick. Sometimes we don't want to execute the field right now and want to execute it a little bit later. In this case, we can tell the execution engine that this field is lazy. In this case, the execution will be postponed until all non-lazy fields are executed. And then starts executes fields lazy stage, which does the same thing, but with these lazy fields. And it can also go to the database and so on. As soon as we're done, so all the fields are resolved, we have the query result object, and the only thing we need to do is to send it to our client. So we have to make it JSON and send it back. So that's it. This is the query path. So this is our plan for today. We will start with different ways how to find out the bottleneck in your application. Then we will discuss how to fix common issues that usually happen in GraphQL applications. And in the last part, we will discuss some advanced techniques for specific cases. So first of all, it doesn't really make sense to optimize things before you have measurements. So if you do not have measurements, we have to set up them first. In our Ruby applications, we usually use different services like EuRuKo, but they are not really helpful in terms of GraphQL because, as we know, all of the requests come to the /GraphQL endpoint, so all the data will be aggregated. So we cannot tell which exact query was slow. So in order to make it work, there is a built-in feature in Ruby GraphQL called Tracer. Tracer allows you to fetch events from execution engine and do things with it. For instance, we can just send it to our tool, for instance, to the EuRuKo, and in order to make it work, we just need to turn on the plugin in the schema. As soon as it's done, we can see that we have all the stages we discussed before in the EuRuKo, so we can find out what query was slow. If you use your own monitoring, for instance, Prometheus, you'll have to set up things by hand. And there is a set of gems I can recommend. It's called Yabida. It's created by my colleague Andrei Novikov. The idea is that you can declare all the metrics you want to collect from your applications from different components, from Rails, from Sidekick, from GraphQL, and send it to any data source you want, for instance, to Prometheus. For instance, in case of GraphQL, it sends GraphQL fields request count, GraphQL field resolve runtime, query fields count, and mutation fields count. So it gives you some visibility of what's going on in your application. Now, I wanted to take a break and recommend one book I've read one day. It's called Production Ready GraphQL. It contains a lot of helpful tricks, and some of them will be in my today talk. And this is one of them. It's called client headers. So it's very helpful when you have clients that are not immediately updated, for instance, mobile apps. The problem is that you might find a slow query and fix it on the client side, and then it comes back to you again. And if you have no any client headers, you won't be able to tell if it's a new problem or it's an old problem. So the solution is to add two headers, client name and client version, so you'll be able to find out what client sends you the request. Okay, so now we have our monitoring set up. And it helps us to find out if our query is slow. But sometimes your query is fast, but under certain conditions, it becomes really slow. For instance, if you send a specific variable. In this case, monitoring won't help us, and we need to use a different tool. For instance, one day I had an issue. Imagine a list of items you can buy, and each item has a price in USD. But you want to show it in the local currency for the user. And this query that returns items with prices was fast, but sometimes, according to logs, it was really slow. So this is one of possible ways to fix the problem. Imagine the tracers feature I've told you before. So we can write our custom tracer. So tracer is just a class with a single method called trace. It accepts a key, it's a name of the event, and the data. It's a hash, and contents of the hash depend on the key. So what do we do here? We remember the time when we got the event. Then we let execution engine to execute this stage and compare the new time with the previous time and log it. So we'll see all the stages with time which was spent inside the code. So this is how it looks like. We can see that we have an execute field which is really slow, but we don't know what field is slow. So let's try to find out. I've changed my tracer for a while, so I compare the key with the execute field string, and if it's the execute field stage, I just print the field name. Let's see how it looks like in the console. So we can see that field 1 is slow. So now we can go to the field 1 and find out what's going on. If you're curious what was my problem, the problem was that we had all the conversion rates for currencies in Redis. And when we tried to execute the field for a first time, it went to Redis and loaded a lot of data. So it took a lot of time. The fix was easy. I've just removed all unneeded data from the Redis, so it became quickly. And I have no idea how I could fix it without Tracer. One more cool trick is called directive profiling. There is a link at the bottom. You can check it out later because I'll post my slides later today to the Twitter. So in short, the idea is that you can write a custom directive. In this case, it's called PP. that will apply any profiler you want to the field, and you can try it out on the staging or even on production. It will execute the profiler and put the result to the txt file on server, so you can go and check out what exactly was going on at that moment. This is the part of the implementation. So we have 3 possible profilers for memory, for stack, and Ruby profiler. We start the profile when we see the directive and let execution engine to resolve the field. And then we collect the results and put them to the file as I said. So it's sometimes helpful if you want to find out what's going on the real machine. Okay, now we know where is the bottleneck, and let's fix some common issues we can face. And let's start with parsing. One day when I was preparing to the Ruby Russia back in 2019, I was curious how slow parsing could be. So I've written a small benchmark. This benchmark had a list of queries to test, and these queries were generated using 2 variables, fields and nested levels. Nested levels is how many times we're going to add a nested field to the existing field, like field 1, nested field 1, and so on. While fields count means how many fields we have on each level in the selection set. So for instance, if we have 2 fields with 1 nested level, you will see the following query on the slide. And here are our results. So when we have small queries, it's almost free. So it's happening immediately. However, if we have 4 fields with 2 nested levels, which sounds like a real query, it's possible, it takes 3 milliseconds, which is also acceptable. But if we have 8 fields with 4 nested levels, which is a huge query, it takes a second, which is unacceptable. So it's too much time to spend on parsing, and we'll have also resolved this thing. So you might say that it's not possible to see such a huge query, but I will show you the example a little bit later. But for now, let's specify that we should keep our queries simple. There is no way to reduce parsing time right now another way. The second problem to mention is response building. Sometimes response building is slow because the response size is really huge. There is a link to the issue where the problem was in the huge response, and profiler said that most of the time was spent in the library code. So the problem was not because of developer rather than because of library. So there is no way to fix it at all, and we have to keep our responses small. There are different tricks to make it happen. For instance, if you have huge collection, you should always use pagination, because otherwise it would be possible to load half of the database. Also, you can apply max depth and max complexity arguments to your schema. Max depth limits the maximum depth of the query, while max complexity allows you to specify some fields you want be executed separately because they are too complex to compute. One more trick, which might be obvious but still very helpful, is to keep GraphQL Ruby on the latest version. So when I written my benchmark back in 2019, I've executed it and I recorded some results, and now I tried to execute it again after 2 years. So the benchmark itself was very simple. I've tried to execute a simple query with 6 fields 1,000 times. As you can see, after 2 years, it works faster and consumes way less memory. So it comes for free. So update GraphQL Ruby. One more popular problem is the database. So database can become a real bottleneck because of 2 things. The first problem is that your queries might be suboptimal. In this case, you have to make your queries better, and it's not a topic of today's talk because it's a huge thing by itself. While the second thing is a huge pain for GraphQL users. It's called N+1. So N+1 happens when you have a list of entities with the association. If you forget to load the association, you will make one query to load the list of entities and end queries to fetch the association for each entity member. So how can we fix it in GraphQL world? There are a lot of ways. The simplest way is to request everything from database using includes or EuRuKo. And this works fine for small applications, but of course, it's not that effective because you sometimes load things that you don't need. It would be nice to be able to take a look at the query and decide if we need this association, and this is when we can use a lookahead. Lookahead is a special extra built into GraphQL Ruby application. which allows you to ask the query if it needs to load a specific field. If, for instance, we need to load the association, we can preload it. Otherwise, we can skip it. This is more flexible, but it's very verbose because we have a lot of associations and we have to make these checks every time we work with associations. There is an alternative approach called lazy preloading. It's similar to a preloading, but the idea is that we do not load associations until we access them for the first time. So we list these associations as usual, but then loading will happen only when we try to access it. There are a lot of gems that implement this feature, and I have my own implementation, which is called AR lazy preload, so check it out if you're interested. And there are a lot more ways to fix this issue. For instance, lazy resolvers, batch loading, built-in data loader, and you can check out my article about this topic in Evil Martian's blog. And now we're coming to the last part of the talk about some advanced techniques which can help you to make your application fast in some specific cases. So first of all, let's talk about HTTP caching. HTTP caching allows us to avoid loading the data from database when we know that our client already has valid data. There are some different ways to do that. For instance, we have cache control and expires headers, which allow us to specify the time that the data will be valid. So if we specify it for our response, the browser won't even make the request until it knows that the data is invalid. The second way is to use last modified and if modified scenes. So we send the client the moment when the data was modified for the last time, and it will send us back the moment when it fetched the data, so we can decide if we should send it the new data or just keep it as is, so we won't go to the database. And the third way is eTag. It's similar to the second approach. The idea is that we send client a special, let's say, hash of the data, where we can decide if we should give it the new data. So it sends us an old eTag, and we can decide if the data is still valid. So this helps us to avoid going to the database, but the problem is that HTTP caching doesn't work for GraphQL because of post requests. Post requests are prohibited to use with HTTP caching because of the specification. How can we fix that? It's very simple. We can just allow GET requests to our GraphQL endpoint. When we do that, we can build some HTTP caching from scratch. So imagine the situation that you have a list of banners which are not frequently updated, so it's fine for clients to keep them valid for a day. In this case, we can find out that client requests banners, for instance, using operation name. Then we call a stale method, which will compare the past eTag with the current eTag, which is built based on the date. And if the eTag is the same, we won't even go to the block, so we won't call GraphQL schema and don't go to the database. So in this case, HTTP caching works. However, the problem with GET requests is that it might be hard to put a huge query into the query string, and some browsers won't even allow you to use such a huge query string. So we should make it shorter. And there is a way to do that. There is a special technique. It's called Apollo persisted queries. The idea was very simple. They wanted to send a hash of the query instead of query. Server receives the hash and goes to the storage where he stores all the queries with hashes and tries to find the query. If the query is there, we can just use it as usual. Otherwise, it returns the error to the client, so client has to send the hash and the whole query string. In this case, backend should have to store the query string with the hash and process it as usual. And from this moment, it will know this query, so we won't need to send the whole query again. Of course, there is implementation for Apollo client and Apollo server, but what about GraphQL Ruby? There is a built-in implementation, but I guess it's still in the pro version. And I have my own implementation. It's called persisted queries. So the only thing you need to do is to install the gem, add the plugin to your schema, and pass extensions to the context. Extensions contains the hash of the query. This gem does the whole thing. So it stores your queries in the storage, loads them when we receive the hash, returns the error, and so on. So it works from scratch. And now let's take a break and talk about a special client technique called client batching. It's not the same batching we discussed when we talked about N+1. So the idea is that sometimes it's easier for client to make a single request instead of multiple requests to GraphQL endpoint. So they collect all the requests that would be made to, for instance, to draw a page and send a single network request. So this reduces the amount of requests you get. But remember I said that it's not possible to see such a huge query with 8 fields and 4 nested levels for parser. Now it's possible because we can get an endless request. So imagine the situation that you have client batching and you have problems with parsing. And the only way to fix it is to skip parsing. Let's try it out. So the idea is that now with persistent queries, we get a hash of a query, and then we get the query string from cache and parse it. But it doesn't really make sense to parse it every time because we have a hash and we have a query and it's all the same. So what if we parse the query and put the abstract syntax tree to the cache? That's also possible, and this technique is called compiled queries. So you can read about this technique in the book I've shown you or in the internet, but to make long story short, GraphQL persistent queries gem supports compiled queries from scratch. So we can just turn the option on and it works. If you wonder how fast it can make your application, there is a benchmark. So this is how it was executed. There was a query with 2 nested levels and a single variable, the amount of fields. For instance, in case of 2 fields, you will see the query on the left. There were no database, so each field returns the constant. And I've tried to execute it on different selection sets. For instance, starting from 100 fields, compiled queries make your parsing twice faster. So that might be helpful if you have huge queries. Now let's talk about response caching. So remember we talked about GraphQL caching with HTTP. It's possible, as we know, but the problem is that in GraphQL world, client can request anything. And queries can be very similar, but a little bit different. And in this case, HTTP cache will have to keep 2 versions of almost the same thing. So for instance, imagine the situation that you can request a current user with the display name and the avatar URL. And also you can load a list of tweets with author, and author fields are the same. If you got some data about the current user and then you load tweets, it would be nice to skip loading the information about the author if the author is a current user. But we cannot do that because we cache on the HTTP level. So the solution is to try to cache parts of the responses. This is the idea. When we execute field or even execute field lazily, we have some unique ID of the current field. That's called fragment key. It can be built from the schema version, the path to the query, variables, and so on. So if we have a fragment key, we can build some kind of cache store where we can store result JSONs. When we start executing field, we can go to the cache store with this key and try to get this JSON. If we have this JSON, we can skip executing the rest part of the subtree and move forward. Otherwise, we will resolve it as usual and then keep the JSON in the cache. Of course, there is an existing gem that does that. And it's called GraphQL cache. As you can see, the only thing you need to do is to add a keyword argument cache true, but the problem is that it doesn't work with the interpreter. Interpreter is a brand new execution engine in Ruby GraphQL, which exists for a year now. So I wanted to use the gem, but I couldn't. So I had to build my own implementation, and I tried to find out why it doesn't work. The problem is that there was a mechanism to interrupt executing the subtree when you know that you already have the JSON and it was broken because it was the monkey patch and the code had changed since then. So I had to write my own way to interrupt the execution. And this is the helper. It's called raw value, and there is a pull request. You can get some details about it. So on the slide, you can see a very simple caching. Imagine that you have a list of banners, and you somehow already have a list of banners in the JSON format. So you can just call raw value plus the array or JSON, and you are done. It won't go deeper. Now, when we have the helper, we can write our own implementation. So what I did, there is a gem called GraphQL fragment cache, and it does the exact same thing as a previous one. So you can add a cache fragment true to any field. It will try to load it from the storage first, and then if it's missing, it will execute the field and remember this fragment. It also supports various features like cache expiration, different cache stores, and so on. And I think it's almost it. So let's sum up. First of all, make sure to set up monitoring before doing any optimizations. Then, if you have some problems with the exact query, you can use your own custom tracer, and you can even execute it in production in the console. So it's a very helpful tool to find out what's going on. If you have some problems with parsing, you can either simplify your queries or try to use compiled queries. Make sure to eliminate all endpoints you have, because otherwise it can become a huge problem. Also remember that small responses are serialized faster, and there is no way to fix it, so keep them simple and small. Also remember that HTTP caching is possible if you wanted to. And also, if you want to cache parts of the responses, you can use fragment caching. That's it. I'm ready to answer your questions. I will post slides later to the Twitter, so make sure to subscribe. And thank you for your attention.
Thank you, Dima. And once again, I'll be dropping your links to the stream chat, or if you are attending on that side of event, you can also drop your links there too, so we find you on social media. We have a couple of questions here, so are you ready to face these and give us some answers?
Yeah, sure.
Yes. Are there cases when GraphQL is better than REST and vice versa? Or is it just more about the preference which one to use when talking about the performance?
Well, this is a huge question, and I really suggest to take a look at my previous talk. It was in slides, but in short, it's about the developer experience. Because, for instance, in GraphQL, you have the documentation out of the box, so you don't need to do anything else. You just use GraphQL, and you have documentations valid because it's built from the schema, and you have to keep schema always up to date. And also, it's helpful for frontends because they can request things they want to request without asking you to add something, because you usually allow them to fetch anything they want. So basically, these are the features that can be helpful for any developer. But sometimes it can be an overkill, for sure.
Okay. And then we have a question about the pagination. Is pagination more difficult with the GraphQL API than with a REST IPA?
Well, pagination is difficult by default, and it doesn't really matter if you use GraphQL or REST. So in GraphQL, there is a popular concept called connections. It came from the relay, and it's not the part of the specification, but it's standard right now. So you just have to return your relation in the special format. It returns a previous cursor, the next cursor has next page, has previous page, and so on. So it's very helpful when you need to do the endless scrolls, for instance, and it also doesn't really depend on limit of set, so you can use any cursors you want. So it's not difficult at all.
Yes. I hope you get to see the chat soon, because there's lots of thank yous and lots of good discussion around this talk, and a lot of standing ovations to you, Dima. Thank you for your talk.